Hello, and welcome to the third and final lecture covering the third and final section of Chapter 7, all about introducing the solar system. We've talked so much about all the interesting facts that start to explain the solar system, or at least grab our interest, and extensively talked about the ideas of comparative planetology and the patterns that we see in our solar system. But let's take a minute to appreciate what we've done in terms of direct exploration, because we've sent a lot of robotic probes under a number of different types of missions out into the deep reaches of the solar system. So let's answer one interesting question about the marvels of engineering achievements along with scientific achievements, and that is, how do robotic spacecraft work? A big question, so let's touch on it. Okay, well, we have landing spacecraft that go through incredibly complex procedures that have recently come to a impressive level with modern landings, where recent landings, multiple landings across different space agencies, not just NASA, but mostly NASA, have been using these jets to slowly lower down a basically part of what had been a space probe traveling millions of miles through space that recently had descended through the orbit of Mars, released a series of different parachutes to decelerate and slow down. And what is shown here, what I have an arrow drawn to, is one of the last remaining pieces after jettisoning off parachutes and various shielding that was used during its travel through space. And once all that has happened, there's a timed firing of rockets pointed down to generate upward thrust, upward force, and therefore slow the craft down until it comes to rest, becoming a hovering crane system, hovering for a period of many seconds, some fraction of a minute, and maybe it's a few minutes, so some prolonged period of time, where it will then lower down the robotic rover, okay, a complex robotic rover with a whole suite of sensors and equipment that communicates back with Earth regularly. And this rover is somewhere between the size of a smart car and a normal size car. This is a very large rover. So it's being lowered down by cables and gently dropped onto the ground, at which point the cables are broken, and this sky crane system, this hovering last piece of a complex multi-stage trip through space, fires one rocket, so it will throw itself off to the side and land clear, of course, of the rover. So this is the level of sophistication in the most expensive, most ambitious types of space exploration out there. A lot can go wrong. Sometimes it has, but the recent successes, have been incredibly noteworthy. All right. So that on the very high end, the incredibly difficult to engineer, incredibly expensive, so much manpower, so much expertise, all of that, well, is one extreme. On the other side is, well, how can we gather data without going that expensive? How can we make a more affordable, still obviously we have to spend a lot of money on fuel to get out of Earth's gravity, which is its own issue in the viability of space travel, space exploration, let alone space travel or space, well, I guess, gathering of resources, space, doing actual meaningful work in space. But regardless, in terms of the exploration, we have flybys. All I mean by a flyby, all the book means by a flyby, is no landing, no orbiting. So this is a space probe that has been given a trajectory, given enough velocity, escape velocity from Earth. It is now out, almost like it's going to be an orbiting planet around the sun, but it doesn't have a stable orbit. Instead, it's taking a large swing that would eventually become some type of stable orbit, depending on its interaction with other planets out in the solar system, where it can either gain or lose momentum, which would maybe bring it into a large elliptical orbit around the sun, or fling it out of the solar system, or potentially become an orbiter at the end of its journey. And I'll circle back around to that idea, right? But certainly it allows a space probe to see a lot of planets on the cheap. And on the cheap, just, huge amount of less technical expertise needed here. All right. But the issue with flybys is the time is very limited. The recent amazing amount of images and data that was gathered by the Deep Horizons, or the Far Horizons space probe that went out into past Pluto, did a flyby right past Pluto. It never orbited around Pluto. It just flew right past it. Some amazing images were published from that, and like I said, a lot of data. But that's just it. It was just a few minutes of time as that space probe went past, because there's just such a small window of opportunity. And the same thing here in the case of the Voyager 2, which is currently one of the furthest space probes from Earth, one of the and from the Sun, way out past the orbit of Neptune, deep into the Kuiper Belt, right? So this amazing achievement has been traveling for many decades. And when it was launched, it was a particularly special timed moment that doesn't occur very often, where it was able to slingshot around not one, not two, not three, but four planets, gaining momentum, and thus gaining relative velocity to the sun. So achieving enough velocity to completely escape the sun, not just Earth, with those series of four flybys. But it's not just the energy gained, this idea of slingshotting, it's the data and the pictures. It was this was a very important, very early space probe of actually getting our first close-up images of these planets. So some of these flyby missions, as I said, will actually become orbiters. They don't all follow the same legacy, the same trajectory as the Voyager 2, or the Far Horizons space probe I was talking about, that is also on its way out of the solar system, which is not something that's going to happen anytime soon. And what exactly is the edge of the solar system is an open question of debate. And even if it was to get to the very edge of the solar system, it'd be, well, hundreds of years, to be frank. But they're going to continue to travel and get further and further away, and and scientists will continue to communicate with them as long as they can. But that's really the exception to the rule. Some flyby space probes ultimately crash into a planet. They reach their end of their operating period, and they're given a certain change in their trajectory, where they will get caught in the atmosphere of a planet and then ultimately fall into that planet. That was the case, for example, of the Cassini space probe. That was a flyby around many of the Jovian moons, and then also an orbiter around Jupiter for a while. The Galilean moons in particular, Jovian moons of Jupiter. But regardless, the idea then is that some flybys become orbiters, although on the other hand, some missions are specifically designed to just have a path, escape Earth's gravity, and then just get into orbit around another planet. In fact, on the scale of interesting scientific space exploration, there are some missions that actually are putting orbiters around other planets to just help with future missions, almost like building a satellite network, but not around Earth, instead around another planet. It's actually only being done on a small scale because it's expensive, of course, right? And this is deep space exploration, but to have permanent satellites around Mars, more and more of those are coming up, and then also around the moon as well. So that's an interesting side of an orbiter, maybe that it's not, its primary mission isn't even to take more data, but just to help other future exploration missions. All right, so it's orbiting around another world. Most of them, will go on for a few years. Right, famous orbiters around, in particular in recent decades, the last 10 years, Jupiter and Saturn. Right, so we've learned a lot about those giant planets. We haven't had extensive orbiters around Uranus and Neptune. Not recently. There has not been a focus. It is a very long mission. We're talking over 10 years to get there, on that scale, depending on the positions of the planets. So But there's been lots of orbiters around Venus, for example. So a lot of this approach to learning about the solar system. All right, and the time is key. And sometimes it's months, sometimes it's years, right? Sometimes many years. So it can be lots and lots of data. This is can result in detailed mapping of the surfaces. We have detailed maps of Mars, detailed maps of the surface of the Moon, detailed maps of the surface of Venus. Those come from long-term orbiters. All right, and we've actually even orbited around some of the moons out in the deep space, and there'll be more of that. There'll be more future orbiters and even a lander going to Titan. So we'll learn more about some of the Jovian moons. All right, Titan being a moon of Saturn, a very large moon. So as I mentioned in the first picture, which I went into some detail with, that the pinnacle in terms of ambition at least, and also just the sheer amount of detailed data are landers. I mean, these rovers that NASA in particular has recently sent a kind of a series of rovers that are very much a one model being the next upgrade from the previous one. Currently, there's two rovers operating on Mars, one well past its original estimated amount or the number of years of operation, which is the Curiosity rover, and then the Perseverance is the more recent rover, which is just beginning its many years of research, including bringing a helicopter with it, which has been a great success. It has flown, taking pictures of the rover itself from above, but also being able to scout around where the rover will do its next series of experiments and research, data gathering. And then just doing some of the helicopter has done some of its own data gathering, being able to fly up high and take pictures of the horizon and so on. And what's so interesting also about these landers is this very most recent one is gathering samples in tubes, and it has a whole essentially system within the belly of the rover where all those tubes are stored. And in a number of years, 5 to 10 years, the plan, along with a team effort between NASA and the European Space Agency, is to retrieve those probes with another lander that comes with a launching system to essentially toss the probes up into orbit around Mars that get caught by an orbiter and then shot back to Earth to be delivered to Earth safely down through a slowing into our atmosphere, parachuting to the ocean, getting picked up, brought to a lab, and here we have a series of direct samples from Mars. Samples of rocks that were interesting, samples of rocks that might have dead microbes in them, because remember, Mars was covered in water. And that type of detailed research to be able to see if there's remnants of life on the microscopic scale, to look for DNA directly, that sort of thing, that can't be done on board in the rover. Hence, this incredibly long journey of trying to get the samples back. So really, biggest space missions, of course, involve some sort of actual landing of probes. Although I guess the elephant in the room is, we haven't talked about sending people. Obviously, people offer a even next level ability in space exploration. What humans were able to do on Mars with be able to the number of things that a human can collect it still is so much more efficient, so much more nimble, and pattern selective than any robot can do. They can make decisions. They can be an expert in their own rights. Right? We have to worry about communicating with the robot. So manned missions, such as a manned mission to Mars, obviously is also a direction that space exploration is going in, and a lot of people want to see it go in that direction. All right. So sample return mission, okay? We've done it on the moon with humans, okay? But as I mentioned, that amazing plan to bring back samples from Mars, it's not unique because we've also been doing it with asteroids. The Hayabusa was incredibly successful, going to an asteroid, landing on it, taking samples, bringing those back. It's been done with a comet. It's going to be done again with an asteroid. I think we're going to see a lot more missions going to asteroids and bringing back samples. So that is refining the engineering. There's a lot of countries are focusing on these sample return missions, including the moon and back, because the gravity on the moon and especially on asteroids like Hayabusa, is very low, which makes not a lot of fuel costs to both land and take back off. Mars is a different story, hence the incredible amount of detailed work between NASA and the European Space Agency, and the possibility of it all going wrong, but trying to pull that off. But at the same time, maybe we can not just do it on planets like Mars, but maybe more sample return missions to other moons, those very interesting Galilean moons, those very interesting other Jovian moons, because they would have, maybe a longer trip, but certainly not as much fuel to land and take back off. All right. So bringing those samples back to Earth, and they get very safely sealed up. The amount of concern about contamination, both from going from Earth to the sample, so we never know what the sample originally had, but also we don't want to accidentally release something in case there is alien life in some rock that we brought back just by chance. So there's a very good amount of sealing both ways. So what have we learned in this section? All right, well, we talked about the 3 types of missions: flyby, the cheapest, okay, but smallest window to gather data, least detailed data. Orbiters, that's great. You can spend a lot more time, collect data over months and years. And then landers can last for years, might not. Some of them are rovers, some of them are stationary. Didn't mention that, but some of them are stationary. But regardless, they have a lot of time, and they're right there on the ground, which just is a whole nother level of detail. Seeing, it obviously only relevant to terrestrial planets and moons, but being able to gather so much data right there on the ground, and maybe even collect samples and bring them back to Earth. And wouldn't it be great if you had actual astronauts doing it somewhere other than the moon, going all the way up to Mars, gathering Mars rocks, and coming back home? All right. Okay, well, I hope this section has been interesting, and I hope the whole chapter has. Thank you so much for watching.